We'll use the same information from the last problem and find the rate at which the angle of elevation, whoa, what? Okay, let's draw it again. And we're dealing with the angle of elevation. That would be the angle at which you're looking up to see the plane from the little radar tracking station that we had right here. At the moment that the radar tracking station makes with the plane, at the moment that the radar makes with the plane at the moment that, wow, that's not very well worded. All right, we'll fix that in the future, but in the meantime, we want to basically use the same information as when C equaled 13, which is all the stuff that we had here. So at that same moment, I had to read that a couple times. At the moment the radar tracking station makes with the plane, at the moment that, what? Okay. But basically, we have tons of information at our disposal. We know that A is 5. We know dA dt is equal to 0. We know C is 13. We know dC dt is equal to negative 300. We know that B is equal to 12. And we know that dB dt, even though the speed of the plane is 325, dB dt itself is negative 325. So we have a lot of stuff we could do here. And so let's use some trigonometry, and obviously here's our right angle. So with the trigonometry, we could say, well, let's use tangent and opposite and adjacent. We could use adjacent and hypotenuse and have cosine. We could also do opposite and hypotenuse and have sine. There's a lot of things we could do. I am actually going to, I've worked it out where I did tangent, but I might go a little bit different on this. Let me tell you what we should do. In the process of whatever we do, and this is not like a hard and fast rule, but it's going to help us in this particular situation. In this situation, we're going to eventually need to take the derivative of like things, and the more times you see 0, the easier your computations will be. So let's use this side for sure, which would be opposite. And so opposite and adjacent if you want, or opposite and hypotenuse, either one. I'm going to go opposite and hypotenuse. So let's just say that we really have the sine of theta, which is equal to A over C. Nobody is surprised at that. We'll do that. So let's just take that and run with it, okay? Let's just run with this idea right here. We're going to take the derivative of both sides. When I take the derivative of sine of theta, I get cosine of theta. Wait for it. D theta dt, okay? Equals, the derivative of A over C. That's the quotient rule. So f prime g minus f g prime all divided by g squared. Let's start plugging things in. We need to know the cosine of theta. Wait a minute, we don't know what theta is. We don't know. Okay, well, sometimes you have to stop your calculus and do your algebra, so let's do that. Let's do some algebra here, and that algebra is actually more trigonometry. And I'm going to use that same equation. I'll bring it down here, and I'm going to say that sine of theta is 5 over 13, and I need to find out what theta is. So I'll grab a calculator, and we are going to be in radians, not degrees, so let's make sure we're in radians, and we are. And we're going to do the inverse sine of 5 over 13, and we're going to get that to be our radian measurement. Now, as we look at that, we realize that's kind of odd. It's not in terms of pi, and that's fine. It's totally okay. This is radians, and we're going to store it, again, because as we use this in the future, we don't want to ever just truncate it. We don't want to round it off too soon and miss some accuracy. So we're going to store it. We'll press STO, S-T-O. It's above the on button, and we will go to theta. Theta is the 3, actually. Alpha and 3, and now it is stored. So I'm going to write it on paper, but as I move forward with my computations, I'm going to use what my calculator got. So theta is 0.395. Okay, good for us. We now know what theta is, but I'm not just going to use 0.395. I'm going to use everything in my calculator as we move forward. So cosine of 0.395. Suddenly we're writing in purple. D theta dt, because that's what they're asking. Like, they want to know at what rate this is changing. So if we did an old strategy that we had done in some previous problems, we'd list everything we knew over to the side, which we kind of have, but we would also say, well, you know what? They're asking at what rate the angle of elevation changes at the moment that the radar tracking station makes with the plane, at the moment that, you know, wordy as it is, they're asking for this. That's it. Equals, okay? d/t is 0, lucky us. C is 13, doesn't matter because it's about to get multiplied by 0. 5 times negative 300, all divided by c squared, so 13 squared. Let's solve. It's going to be pretty straightforward at this point. So d theta dt is equal to, all right, 5 times 300 is going to give me 1500 over 13 squared. I'll go ahead and call that 169. I know that, and you know that. So 169. And we need to divide by the cosine of 0.395, which is really cosine of theta. So again, we're going to use our calculator for that one. So here we go. Let's do this. 1500 divided by 169. Okay, this is going to be wrong. Trust me, it's wrong. Cosine of theta. Wrong. Okay, and here's how it's wrong. It's not because I left that parenthesis off. That has nothing to do with it. When I'm dividing by this, I'm dividing by everything. So we are going to need a couple things. Either parentheses around those, or we're going to need to type it a little differently. We'll go 1500 divided by 169 and also divided by the cosine of theta. Either way, it'll work. So either one of these is correct. This is not, because again, we did 1500 divided by 169 times cosine. We're dividing by both of these things, either represented with parentheses around the multiplication or divide and then divide. So let's write it down. D theta dt equals 9.615. We can really round it off now. And if we want to put units, we are dealing with the rate of change of the angle, which is measured in radians, and it is per hour at that specific moment.